And so, thank you for the presentation, and thanks also the organizing committee, especially Edgar and Damian for the invitation. And today I will talk about a system for beams and plates and a Lagnese-Lions conjecture. And here I will present was made some result in collaboration with Professor Fagner Aruna and Pablo Braz. And so my presentation is divided into three parts. In the first one, I will talk about some beams model. In the second one, I will present Lagnese-Lions conjecture. And finally, I will introduce another important result. And so, let's consider initially the one-dimensional linear Milet-Timoshenko system. This is a system, a model for beam, and this system is widely used due to physical applicability. And here we have the Cartesian 0L times 0T, where 0L is the segment occupied by the beam, L is a positive number, and T a positive time. And here we have also the component PC, which represents the angle of rotation. Psi represents the vertical displacement of the beam, and more, we have H, a positive constant, which represents the thickness of the beam. Rho corresponds the mass density per unit volume, and finally, K is the elasticity in the shear. We are interested to study this problem subject to appropriate boundary conditions, but it's interest to comment that in 1988, Lagnese and Lions proved that in the linear one-dimensional case, the solution of the Milet-Timoshenko system converge as k goes to infinity toward the solution of the von Karman system. And so in the same book, they also conjectured that in the nonlinear b-dimensional case for the Milet-Timoshenko system, it's expected that when we pass the limit as k goes to infinity, the solution of the b-dimensional nonlinear Milet-Timoshenko system converge in some sense for the solution of the b-dimensional nonlinear von Karman system. And so we have here the part of the book where the conjecture was made. And it's important to see that the conjecture was made for the b-dimensional case. But let's start understand what happens if we consider the one-dimensional nonlinear Milet-Timoshenko case. And here we have another beam model, and we can see that here is a complete system, and in addition to all components above, we have also the component eta, which represents the longitudinal displacement, and D is the modulus of rigidity, and finally E corresponds to the Young's modulus. Okay. The first work that appeared with intention to give a defined and a positive answer for the Lagnese-Lions conjecture was the work in 2010 by Araruna, Braz e Silva, and Zuazua, where they proved that, in fact, if we consider the one-dimensional, nonlinear Milet-Timoshenko system, but here they study the system with regularism term here. And in fact, when we pass the limit, the solution of this problem converge as k goes to infinity toward the solution for the one-dimensional von Karman system. And we have here the one-dimensional von Karman system. And the proof for this result, this convergence with the regularism term, I can say that they prove partially the conjecture, because the conjecture was made by Lagnese-Lions states that the Milet-Timoshenko system converge as k goes to infinity for the von Karman system without the regularism term. Okay, and this work solve partially the conjecture stated by Lagnese-Lions. And here we have the main references for the first part of my lecture. The first one is the paper where the authors studied their one-dimensional nonlinear Milet-Timoshenko system, and they gave a partially answer for the conjecture. And in the second one is the Lagnese-Lions book, where they studied the one-dimensional linear case, and they conjectured the limit of the Milet-Timoshenko bidimensional nonlinear case converge as k goes to infinity toward the solution of the von Karman system. And so, from the mentioned work of Araruna, Braz e Silva, and Zuazua, some questions has appeared. And consider now the one-dimensional nonlinear Timoshenko system here. And the first question is about the veracity of the conjecture. And in the second one is what's the difficult to solve the Lagnese-Lions conjecture without the regularism term. Okay, and now I'm on a way to prove that the convergence is true, but keep calm. Let's understand what happened with the one-dimensional case. Okay, so here we consider the one-dimensional nonlinear Milet-Timoshenko system here without the regularism term, and more, we study this system with these one boundary conditions and initial data. For this system, we have the energy is given by this expression. And for system, we can also guarantee that the energy is conservative. That is, this expression holds for every positive time. The existence of solution for this problem can be guaranteed by this theorem. So, if we consider initial data in appropriate space, then the problem one-dimensional nonlinear Milet-Timoshenko system has a unique solution in this one class, and more, the energy given by this expression satisfying this condition. The sketch of the proof, this result, is using semi-group theory. And now I will present an important result as the following. Let phi PC eta be a solution of the Middle-Timoshenko system. And just to remember, we have a one-dimensional, nonlinear Middle-Timoshenko system without the regularizing term. And so, if we consider initial data in appropriate space satisfying this condition, well, phi0 plus pc0x is equal to 0, then letting k goes to infinity, one gets the weak star convergence in appropriate space. And here we can see that C and eta solves the von Karman system. And here we have the von Karman system with the boundary conditions and initial data. Let me just to comment that in the Middle-Timoshenko system, we have a problem with three coupled equation, but when we pass the limit as k goes to infinity, we have the von Karman system. It means that we have two coupled equations, and that is the rotational effects are neglected. And just to return here, in other words, we can see that it's like this equation joined this one equation. And so in the limit, we have a fourth order system. Okay? Well, okay. The idea to prove this result is the following. For each k, a positive number fixed, let phi pc eta be a solution for this problem with initial data in appropriate space. And so it's possible to see that the following sequences are bounded uniform on the time and in L2 of 0L. And more, we can see eta something like this, and now since eta t is bounded uniform on the time in L2 of 0L, we can guarantee that eta is bounded uniform on the time and in L2 of 0L. Okay? And with this, we can start in subsequence, and one gets this convergence, weak star convergence in appropriate space with phi plus pcx equal to 0. And more, we have this convergence in appropriate space. And finally, we have the convergence of the nonlinear term, and here we have alpha. Okay, if we're using a compactness theorem due to Alban and Lions, it's possible to see the phase of the alpha, the limit for the nonlinear term. And so for A, B, and C in appropriate space, satisfying this condition, that is A plus Bx equal to 0, the variational formulation for the Middle-Timoshenko system, nonlinear, one-dimensional system, is something like this. And here, if we pass the limit as k goes to infinity, we obtain the variational formulation for the Middle-Timoshenko von Karman system, sorry. So in the limit, we obtain the variational formulation for the von Karman system. And with this, it's possible to guarantee that the conjecture made by Lagnese-Lions is true. But we must remember that the conjecture was proposed for the bidimensional case. And so now I will present the Miller-Timoshenko plate model. And here we need to consider the cylinder. K is equal omega times 0L. Here, omega is a subset of the plane and T a positive time. With lateral boundary sigma, and so the bidimensional Miller-Timoshenko system is given by this expression. And here is important to see that in the plate model, we have two rotational angles and two longitudinal displacement. And more, the operators L1, L2, L3, L4, and L5 is given by this expression here. And now I'm interested to study this problem, the bidimensional nonlinear Miller-Timoshenko system with these one boundary conditions and this one initial data. And here, for the boundary conditions, it's possible to see the operators B1, B2, B3, B4, and B5 defined here. Okay. As in the previous case, the energy of the solution is given by this expression, and here you can see the full expression for the other terms. And as in the previous case, the energy for this system is conservative. It means that this expression holds. Well, after all that I told you, I'm finally going to present the most important result of my lecture. And in this result, we have a definite and a positive answer for the Lagnese-Lions conjecture. And so the result is the following. Let phi1, phi2, phi eta 1 and eta 2 a solution of the bidimensional nonlinear Miller-Timoshenko system and initial data in appropriate space. And more, we need that the initial data satisfying two conditions. The first one, phi 10 plus c 0x is equal to 0, and phi 20 plus c 0y equal to 0. And now, if letting k goes to infinity, one gets this convergence, this weak star convergence in appropriate space. And here, C eta 1 and eta 2 solves the bidimensional von Karman system. Here we have the bidimensional von Karman system with these one boundary conditions and initial data. Okay. So recall that if we are assuming the filament of the plate to remain orthogonal to the formed mirror surface, so the transverse equations are neglected, and it means that in the limit we have a system without rotational effects. Okay. Let me just to comment that the proof of this result is following from the previous theorem, considering, of course, the specificities of the bidimensional case. Okay, and now the paper will contain the formal, definitive, and a positive answer for the Lagnese-Lions conjecture, And the other important result is a joint work with Araruna and Bryce Silva. And just to finish, I would like to comment that if about the uniform stabilization. And so if we consider the plate model with internal damping distributed along all the plate here, the energy associated for this problem is given by above, but now the energy obeys this one dissipation law. And we have this one theorem, which means that let phi1, phi2, pc eta 1 and eta 2 be a solution of the Milik-Timoshenko system, and we need the initial data in appropriate space. So there is a constant, there is a positive constant omega such that this inequality holds, which means that the energy associated for this one system with internal damping decay exponentially. Okay. And one remark is about the following. As a consequence of the previous inequality, if we consider the initial data satisfying this one condition and the second one, letting k goes to infinity, one recovers the exponential decay for the energy associated of the von Karman system. Okay, and so just to finish, I would like to see here the von Karman system, bidimensional nonlinear von Karman system, but here we have internal damping, okay? And the energy associated for this system is given by this expression. And let me return here by this remark. If we consider this one and this one condition for the initial data and letting k goes to infinity, it's possible to see that the von Karman system here decay exponentially. Okay, so I'm done. Thank you for your attention.